Good afternoon, and welcome to what appears to be like a presentation that could be of some interest. There's nothing like an absolutely packed room, standing room only, and starting several minutes early. So you, and each one of you, represent the respect that people in this community have for this gentleman to my left, Dan Kaminsky. Dan has been a very important thinker, obviously, in computer security over the last 10 years. He's worked in a number of top companies out there, including Avaya, Cisco, IOActive, and of course Microsoft, where he worked on enhancing the Windows operating system and different projects. I think many of us were here 2 years ago, 2008. I was here when Dan shook the house. And he shook the house when he shared a mechanism to exploit what had been a known flaw, recognized flaw in the domain name system protocol. And while the flaw had been known, it was not thought that that flaw could be successfully exploited for malintent or other purposes. Well, Dan laid that issue to rest, but he did it in a graceful fashion in that he discovered the flaw or worked on the flaw to develop the exploit and then shared that with key industry players, I think roughly up to 6 months in advance of him coming to Blackhat and sharing that fundamental flaw, which shook a lot of this industry to its core because the domain name system is so extremely vital and important to the functioning of the internet. It's an honor for me to be here. I'm Rod Beckstrom, by the way. I'm President and CEO of ICANN, the Internet Corporation for Assigned Names and Numbers, a multinational nonprofit organization which is the coordinator of the domain name system. But when I was here 2 years ago, and when I was speaking and doing the keynote, I talked about how the most important thing we could do for security in the internet was perhaps investing in protocols, new protocol development, finalizing protocols, developing those standards and then rolling them out and implementing them, because otherwise we're just putting a lot of patches onto a system that it inherently was not designed for security. So that was 2 years ago. That was a morning speech I gave. Then later in the day, Dan shook the house when he announced the fundamental DNS exploit. And so it's very exciting at this Blackhat 2 years later, in part because of the industry's reaction to the exploit that Dan discovered. Many parties came together and pushed DNSSEC to a successful conclusion. So it's my honor to introduce Dan, and not only because he's brilliant and has contributed so much, but I really respect Dan for his integrity and for the fact that he really cares, and he's here to help make a better internet and contribute to a better world. So with that, I hand it over to Dan Kaminsky. Thank you.
First of all, I do want to apologize to anyone who's here to see a bunch of stuff on web defense. Although we are out to defend the web, you know, the DNSSEC root was signed 2 weeks ago. If I'm going to give a DNS talk, it's got to be now. So this is now my 11th year speaking at Blackhat. I know a lot of you think that maybe I've got like a thing about DNS. Small one. No, this was not actually my original obsession. No, my actual first talk here was on SSH, the really popular platform for remote system management. My first Blackhat talk, believe it or not, was my first most successful. Code from that talk, the -D flag, is in every Mac and Linux machine on the planet. Someday, perhaps, I'll do something just as significant. So I've been kind of interested. Anyone here notice how excited I've been about DNSSEC for like the last 18 months? This talk is basically about why. So let's start with a very common scene in information technology. Oh crap, gotta log in to some machine at some customer.org site. And it sits there and it looks at you and says, you got a password? And you're like, man, I'm your vendor. Why can't I just tell you I'm your vendor and log on in? And, you know, wouldn't it be nice if I could just say, hey, I'm Dan at remotesupport.org. can I please log into root@somecustomer.org? Wouldn't that be nice if it just, oh, hey, that just worked. All right, well, I guess this required some crazy, complicated configuration on the server side. Oh, hey, that SSH server is configured to allow Dan at remotesupport.org to log in. And that's all the configuration it took. What is going on here? My friends, we live in the future. For the last 18 years, people have been trying to secure the DNS. Believe me, I get a lot of credit, but I did not even do a tiny iota of the work here. But they did it. Now it's our turn to secure everything else. DNSSEC offers us the ability to build some things in security that we've never had the ability to do well before. But I get ahead of myself. There are 5 audiences for the talk that I am going to give now. They're the user, they're the buyer, they're the builder, there's the breaker, and there's one more. If you're a user, you're just someone, watch stuff, maybe you're here hanging out, learning what it's all about. I know you're out there. We're here to build what I call the domain key infrastructure. The domain key infrastructure, what it means to you is that when you receive a mail from your bank, you're actually going to know it came from your bank. We've been promising this to you as a security community for 15 years. We got to deliver. I apologize to you. We should have done this a long time ago. All we do instead of giving you what we say is we ask you too many questions. We make horrible demands on your memory, and we blame you when we screw up. But I'm going to tell you the truth. When we in security fail, it's not because for lack of trying. It's because we've lacked a fundamental foundational element needed to secure the network. If you're a buyer, I'm just going to tell you straight out and bald, DKI is going to increase your budget. Now, 10 years ago, you may have remembered spending hundreds of millions of dollars in your community trying to get authentication under control. Now, on the one hand, it didn't work. Oh, man, it didn't work. On the other hand, it's not like we need strong authentication any less today than we needed it 10 years ago. Verizon Business did this amazing data-driven study, and you know what they found? For all the lead O-Day, for all the cool tricks, 60% of compromises traced back to passwords and credentials. No passwords, bad passwords, default passwords. This problem is not going away, and it's literally 60% of the expense. If you are a builder, meaning you make stuff for people to buy, let me tell you, this is going to refresh your product line. Okay, we've all sold a lot of stuff that doesn't scale. Okay, you can get someone to buy it, and they'll take it to their labs, and they'll run it in a little division. But you'll always note after 6 months, a year, 2 years, they're not really picking up your phone calls, are they? It's almost like once they tried to actually deploy the stuff at scale, it didn't work. Well, you know what? Life's too short to defend broken code. If I didn't think this DNSSEC stuff was actually going to work, man, I got other things to talk about. This is going to work. We are finally going to be able to build out scalable federated systems. Now, if you are a breaker, you are the second most important in this room. Most people believe code is secure until proven otherwise. We know that's not true at all. If you were paying attention to the SSH demo, you probably picked up on the fact, wait a second, Recursion Ventures is making DNSSEC pre-auth in OpenSSH? Yeah, and you're on the right path. We are going to do this. We got to be paranoid. We got to be paranoid like we've never been. And so we're taking the radical transparency route. I am now the chief scientist of Recursion Ventures, and this means I get to say things like, you know what? We are going to fund and work and support an aggressive public audit of all DNSSEC and DKI technologies, starting with LDNS, probably the best DNSSEC library on the planet. You may or may not know Justin Ferguson. If not, you should. The guy's probably one of the best code auditors in the world. He is auditing LDNS for us right now, and we are going to release his report completely, openly, and publicly sometime in the next couple of weeks. NLNet Labs is the author of LDNS. They love it. They are completely supportive and are totally backing this operation. You know what? We have a latency issue in security. We don't find the bugs during development, during early adoption, even during like the standard, spread. But man, once this stuff gets popular, we show up, we're like, oh yeah, that's really broken. Okay, I don't want to wait 25 years for the next DNS bug. We've got to find this fast. So we will do everything in our power to support that. But the most important is Grandma. Grandma, look around. Grandma, wave to the audience, if you will. My grandmother, this is her 7th Blackhat. Gotta say, Grandma's been at more Blackhats than you for almost all values you. And she has brought cookies, so feel free to have some of our family cookies after. So what are we here to do? First, we're here to explain DNSSEC. It's not actually that complicated. Second, we are going to deploy DNSSEC on stage. It is going to be the one live demo I'm going to do here. I will taunt the demo gods but once. I don't have time to discuss everything. It turns out a bunch of code worked at the last minute that I didn't expect. So we can't talk all about how the server-side scalability stuff. But we are going to talk about end-to-end trust and how DNSSEC is actually going to implement it. And finally, we're going to demonstrate the domain key infrastructure working. Not theoretically, not hype, not maybe this is how it could work, right here, right now, on stage, Coder GTFO. Now there's some ground rules. First of all, no religion. I do not care. We do not care about not invented here. Some of the coolest content in this talk was not even my idea. That's fine, because we have an internet to fix. This is a problem that is bigger than any one individual, any one organization, any community, or even any country. We've got to work together if we're going to make this stuff work. We can't care about style. Not don't, we can't. There's something I refer to as Skype Flaw, which basically says the internet got really messed up in 2001, deal with it. Theoretical elegance is great and all, but it's got to work. And not just work, but it's got to work well. Systems that barely work, barely deploy. There's another talk here. I'm horribly embarrassed I don't remember the name of the speaker, but he repeated some research on looking at what is going on with SSL on the wider internet, and you know what? It's just not very good. A million endpoints out there. Half of them aren't even pretending to be secure. I mean, we're not doing a very good job. So corollary is, we can't cite historical precedent all that powerfully. It's not like what we're doing now is working. We do care about operations. We are not going to win this game by calling people lazy and stupid, no matter how intelligent and industrious it defines us as. We're not going to win through moralization and accusing people of being bad people. And we're really not going to win through regulation. We want a more secure internet. We want stuff where users can find out that they're talking to their bank. We're going to have to do this the old-fashioned way, by delivering better products that are easier to deploy, that are less expensive to deploy, that offer value to the people that are running them. Can security do a better job? Let me tell you, this password situation we have is a mess. If we can't do better than this, we're just not trying hard enough. So, timelines. 18 months ago, we were very loud and said, yeah, this DNSSEC stuff is a train wreck, implementation-wise. You know what else we said? It's going to get better. The protocol is actually okay. Now look what we have 18 months later. We have products, a lot of them. We have a lot of open source products. We have a lot of commercial servers. We have a lot of managed service providers. This is not a sales pitch. This is a market description. There is a robust market of companies out there building solutions around this stuff. There's a lot of skin in this game. Now you might say, why does this matter? Well, because I'm out here telling you this is a technology that you can base major aspects of what you're trying to defend upon. If I was out here saying, trust me personally, you know what, I'm some guy. I'm some guy who's up to some interesting stuff, but I'm still some guy. It matters that there is a healthy range of suppliers. This technology has some legs. Now what I am here to do is tell you not simply what other people are doing, but tell you where this technology is going on the 6 to 18-month time scale. So first off, let's begin by talking about DNSSEC itself. You know, it's not that complicated. You ask a question, you get an answer. Or you ask a question, you get a referral. So you go to Alice and say, what's Jenny's number? Says, ask Travis. You go to Travis, say, what's Jenny's number? Says, ask Charlie. Go to Charlie, ask Jenny's number, 876-5309. It's really not that bad. So here's what DNSSEC does. You ready for it? It adds signatures. So, Alice, what's Jenny's number? Ask Travis. Trademark. Travis, what's Jenny's number? Ask Charlie. Trademark. And you might say, no, it can't be that simple. It can't just be a little extra goo at the end. I mean, come on. Is that it? No, I mean, that's really mostly it. There's a little bit of stuff. Referrals now, instead of just telling you where to go, give you a new key, a new way of understanding, okay, go over to ask this guy and here's who he is. So before, you were just told where Travis was. Oh, go ask Travis. He's down by the water fountain. Now you're told, here's how you recognize him. Oh, he's the skinny white guy with the dreadlocks, who's now the chief hardware officer of Recursion Ventures. Welcome aboard, Travis. Are you in the room? Howdy, neighbor. Now, it's not quite so simple. Computers can make stronger identifiers than humans do. Everyone always says, how do I explain public key cryptography? You know what? It's really easy for me to recognize my grandma's face. I'm not so good at looking like her. Bam, you now understand public key cryptography. So, there is some magic here and there. Saying Jenny has no number has some magic. This is what's called NSEC and NSEC 3. And time is involved. So, referrals will only last a certain amount of time and so on. And keys can lead to other keys as well. Some of the magic is optional. A lot more than you'd think. When you hear DNSSEC is complicated, it's because someone thinks the magic's not optional. Now, all of the magic can be implemented in an easily deployable manner. The easiest is have someone else do it. Go to a vendor, get a magic box, go to a managed service provider. However, I don't want anyone thinking you have to do this because the technology is a mess, because it's not. So here's what we're going to do. We are going to taunt the demo gods and we are going to deploy DNSSEC from scratch on stage. Let's do this thing. All right. Man, I've heard this takes like 100 hours. There's no way I have time for that. Luckily, I don't actually need that sort of time. So here's what we're going to do, all right? I don't think anyone is going to be able to read that. So we're going to have to log back in here. See, this is the problem with live demos. Let's do this. This is why the other reason why I can't do all the demos live, because it would eat up all of my time. But I think this one is, if there's one thing that people need to see, that this is just not that big of a deal. By the way, does anyone here know about Cygwin for Windows? It basically gives you a Unix shell on your Windows machine. Eventually. Damn, that's not good. Can I get SSH, please? Maybe. Balls. That one work? Okay, the little one worked. I apologize. You're just going to have to believe me for some of this stuff, okay? So here's what we're going to do. We have a standard server here. It's got a couple of zones in it, like doctorsoffice.org and somecustomer.org and navy-dot.mil.org. And, I think this server should have DNSSEC. Let's see what that's going to take. So, First thing we have to do is we're going to go ahead and, so step 1, make the name server listen on a different port. Named.com. I think that's options. All right, let's go ahead and make that listen on port 5003. That's step 1. We have to go ahead and restart the name server. All right, now step 2. We have to run Freebird, which is a totally new DNSSEC server that we've been developing for a while. So now we've run Freebird. Step 3. There is no step 3. We actually just deployed DNSSEC. So look up at localhost with the DNSSEC flags. I don't know, www.hospitallink.org. Oh, hey, there's actually a whole bunch of trademark extra goo. Man, that really didn't take long. But that couldn't really have worked. I mean, are there DNS keys? Oops, actually, you have to look it up on the main. Yeah, there's a DNS key. There's even a DS key. Huh, this ain't so bad, is it? Now, I know what you're saying. Don't you need to go ahead and talk to GoDaddy? Okay, that I'm not going to do live. Okay, so what do? You go to GoDaddy, put in your zone, say you want to manage DNSSEC, you paste in some numbers, which you got by just saying, look up, in this case, remotesupport.org, look up the DS, you get that value. You say, yep, why don't you push that? You wait 30 seconds, and it's deployed. And there it is, and it worked. And you just deployed DNSSEC in 2 minutes. Now you might be wondering, and by the way, that's an end-to-end DNSSEC resolution that you're seeing right there. So why this works? Why was this so easy? I thought DNSSEC was supposed to be a horrible pain in the butt to deploy. Well, DNSSEC was designed to allow key in a vault approach to security. What that means is every once in a while, you take the magic super key out of the box, and then you update your zone in some great ceremony. Now, why was this model something that the DNSSEC people had to implement? 2 reasons. First, okay, guys, they've been working on DNSSEC for a long time, which means, 18 years ago, 15 years ago, 10 years ago, CPUs weren't very fast. If you wanted to be able to do a high processor task, you had to have a lot of CPU available. And so you didn't want to do this, oh my God, I got a DNS request, let me go ahead and spend 100% of my CPU for 5 seconds. You had to do it all in advance. So that was the first reason. And the second reason is that DNSSEC needs to support systems that operate at scale. When you wonder why VeriSign hasn't signed .com yet, guys, .com is enormous. And they've really needed to push a lot of this stuff to its limits. So that's kind of why DNSSEC needs to go ahead and have offline signing and a lot of the complexity that you might have heard of. But the thing is, offline signings were really expensive, just in terms of the operational contortions that one has to go through. Now, there's been a lot of work to automate this stuff with cron jobs and so on, but it remains complex. Freebird is an online key signer. It doesn't know anything about some larger zone list of names, big pre-computational phases. A request comes in, it's looked at, it says, oh, you want the signature for that name? Well, let me go see what the value is for it. Oh yeah, here you go. I'll sign it on demand. Now, we did not invent online key signing. SSL, SSH, IPsec, most, in fact, network protocols have their cryptographic keys online just waiting to sign stuff. There's a bit of religion here, but I don't care about religion. I care about what operationally works. And in most protocols, what operationally works is having the key online, and if you don't want someone to extract it, you put it in a really good box called a hardware security monitor, or HSM. Now, there's been quiet but very visible support for online signing dotted throughout the RFCs. Thank you, Ben Laurie. We're not the only implementation that is doing online signing, which we found is much easier to deploy. Bert Hubert's Power DNSSEC does it as well, but we do have one kind of neat thing. Yeah, we're a bump in the wire. We're a proxy. You want to have your entire DNSSEC framework running, DNS framework running just like it always has, but oh yeah, throw some DNSSEC in front of it while you're at it. No problem. There's nothing operations likes better than minimal disruption. There's no configuration. You didn't see me provide some big list of arguments to Freebird. I was just like, hey, go proxy that thing listening on 50053. That'll be great, thanks. Our present implementation is a UDP port forwarder. So it goes ahead and just uses full-on application layer forwarding. We're actually building a mode using what's called the Linux mangle table. And this will allow the back-end name server to still see the original IP addresses. However, its responses will just magically inherit signatures. Now, one of the things I said early on was what we did to fix the DNS bug 2 years ago was a Band-Aid. Someday, DNSSEC is going to have to be as easy to deploy as that patch was. Now, this isn't quite as easy to deploy, but man, it's pretty close. Freebird's fast. This is not because of me. This is because the Linux kernel developers, libevent, and especially Niels Provost, are badasses. Check this out. We were talking earlier with some guys at VeriSign. Not so long ago, their entire operation hosted 60,000 queries per second in 400 lines of code on now modern hardware. A libevent-based DNS server a single libevent-based server will handle the entire load that VeriSign as a company used to have to deal with. That, my friends, is pretty crazy. Now, we're not going to be at full 60,000 queries per second because we have a back end to speak to and so on. But without any tweaking, Freebird as a proxy does not seem like it's taking a particular amount of load. It seems to be a couple orders of magnitude fast, at least an order of magnitude faster than the basic servers we're dealing with now. Freebird caches. The reason why it is, so what we do is this. Anytime a request comes to us, we have no idea what the response is going to be. Because there's no reason when you ask the same name server the same thing twice, it has to give you the same answer. So we always pass something to the backend. Backend sends something back to us. We're like, hey, wait, have I already signed this answer? And if so, we don't go ahead and re-sign because that requires computation. We pull it out of the cache. But the actual answer, the actual content, is always under the control of the backend. They might say, well, Dan, why is that a big deal? Well, because you may not have noticed, but most of the really big sites nowadays use content delivery networks and dynamic DNS determination. If DNSSEC meant you had to completely re-architect the way your high-performance site used the internet, you won't deploy DNSSEC. And you know what? I want people to be able to deploy DNSSEC. So that is why we took this particular path. I don't care what you're hosting, we'll sign it. So, it's open. Why is it open? Because let me tell you, you just re-implemented anyway. You might as well use our code. We should have the code out today. We don't because I've been working on mad crazy demo stuff. If you send an email to info@recursion.com, we'll send you a preview copy complete with horrifying remotely exploitable flaws. The actual code should be out in a few weeks, complete, of course, with Justin Ferguson's pen test report. But remember, what we're talking about here is on the 6 to 18-month timeline. This is where things are going, not where things are necessarily at. Now, Freebird does a lot of things I don't have time to talk to you about today. There's a whole bunch of obscura in the DNSSEC realm which you may want to know about. In fact, you may have some axes to grind. Well, how do you handle non-existent records like NSEC stuff? How do you tunnel trusted records to registries when the registrars? By the way, there's this thing in DNS about registries and registrars and registrants. They love the prefix regist. It's really weird. I am not going to hit you guys with that. You'll walk out. Questions like how do you handle rollover and expiration? How do you keep clocks in sync? This is actually a fascinating problem. And if I had 2 or 3 hours, I'd love to go over it with you. But instead, there's going to be far more complete slides posted on recursion.com. Check them out, or come bug me after and hit me with all the crazy stuff. Believe me, we've been thinking about this stuff because we're making some pretty big bets that this is how we're going to secure the internet. At least against a portion of its problems. DNSSEC does not solve everything. So, towards the domain key infrastructure, how do we actually do PKI, but this time it works? Perhaps DNSSEC is easy to deploy, but so what? Distributed authentication is only interesting if it provides end-to-end semantics. Meaning, I've got a machine, I've got a desktop, I've got a phone, you've got a machine, a server, or whatever, somewhere in the cloud. I want to have an end-to-end connection, meaning I don't want to have to trust my local name server. Isn't trusting your local name server and hoping for the best the model of DNSSEC? Well, some people thought it was. The basic mode in DNSSEC is what's called the AD bit. And what the AD bit says is, oh, hey, client, check it out. I actually securely resolved this name. It's cool. You can trust it. Yeah, so? Look, I know Starbucks. I like Starbucks. I drink their coffee. I'm not trusting Starbucks to tell me the certificate of my bank. This I am not going to do. So no application on earth is going to alter the user experience based on the AD bits. What do? It's not enough to just trust. By the way, if you're not familiar with the architecture of DNS, I better explain it now. So the deal is you have this hierarchy, this, you have to go around between Alice and Travis and so on. Well, that's a lot of work, especially if you're a machine from 1983. So what we did is we had these servers called recursive resolvers. And they go ahead and they bounce around and do all this work. And then they come back and they're like, hey, I heard that Alice's number, that Jenny's number is 8765309. This becomes interesting in DNSSEC because here's the question. Do you still go to that recursive server and say, hey, go around and get me some information and tell me what you got? And the answer is, well, if he can be useful, if he can tell you things you actually want to know with a full trust chain, maybe. But at the end of the day, you don't trust them. You want to know and validate for yourself, or you're just going to have to do it yourself. So how does this end up working? How do we get full keys out of DNSSEC from some server on the internet to the phone in your hand? It turns out there are 4 mechanisms. They are chasing, tracing, wrapping, and packing. Let's go through each of them one by one. Chasing, going up the stack. When you have a signature, a so-called RRSIG, say you have a signature for www.foo.com, that signature says who it's signed by. So www.foo.com was signed by foo.com. Foo.com says, oh yeah, I'm signed by com. Com says, oh yeah, I'm signed by root. And then you were sitting there and you know how to recognize the root because the DNS root, as of 2 weeks ago, was finally signed. So now, if you're a chaser, if you're a chasing validator, you don't need to have all these intermediate keys. You just keep hopping back up. You go from the foo signature to the www signature to the foo signature to the com signature to the root signature, and you're done. This works and is implemented in LDNS today, and it takes about 10 lines of code. There's going to be a full sample kit and API implementation in the Freebird release package. But basically, it's a matter of running a few calls. What's the result? Well, here we go ahead, and we're sitting at a desktop, and we say, please chase back spooky.navy-dot-mil.org, and we chase it all the way back. LDNS is so nice, it even renders the pretty picture that you can show in your slide decks at Blackhat. Cool. End-to-end trust. Now, there are two problems with chasing. First of all, it requires you to go back and forth with your local name server. Your local name server is going to keep giving you these little slices of what you want to know, but you have to keep asking. Now, if your name server's on your local network, big deal. But say you're using OpenDNS or Google DNS, the distance between users and their servers is increasing. It's getting slower. And as Paul Vixie says, there's no way to make this faster without patching the speed of light. And that's not happening anytime soon. So, what we've been working on is something that I call SuperChase. And in SuperChase, the actual technical description is that you set not just the CD bit, checking disabled, to 1. You also set what's called the RD bit, the recursion desired bit, to 1. And what happens is when you do both, the server says to you, oh, you're looking up www.foo.com. Hey, why don't I just send you all the records that get you all the way to the root? The server has to know anyway, because it has to go ahead and have that list in order to do its own validation. Why doesn't it just send it to you? And so that's actually what we're looking at, and there are some neat facets for how it'll work. It actually requires effectively no protocol modifications. It's very nice. What's less nice is that there are very non-compliant networks out there. The basic functionality that is supposed to be in your local resolver to allow you to get even the first hop of a chase train. Yeah, it just might not implement that. It might be some little box in a hotel. Man, there is nothing worse than a hotel network. You're lucky you can like browse Google on that stuff. Local network might block traffic. And this is, in fact, your problem. Why? Because it comes back to the ops guy. You have some user who's depending on DNSSEC working. They show up at a hotel, and the network doesn't work. You know what they do? They call the help desk. You know what that does? It costs money. So, ops is king, and if we don't deal with this, hey, you know what? They'll just not deploy the stuff. So what's our next approach? Tracing. Tracing, now look, in chasing you start at the bottom and work your way up. In tracing you start at the top and work your way down. If this sounds like exactly what a normal DNS recursive server does, it's because this is exactly what a normal recursive server does. It just so happens that the NLNet guys took their name server built on LDNS called Unbound, and they said, what if we made lib unbound? What if you could take an entire name server and pack it into a little library that could be called by any application sitting on your phone? This is actually kind of cool. Instead of 8 lines of code, now we're down to 3 lines of code. Basically, you create a context, you add some trust anchors, and you call. And it just comes back and says, oh yeah, I got that, here you go. And you get a very nice API as a programmer to build this into your system. Now what's the problem with tracing? Well, the biggest problem is it entirely bypasses local cache. This increases the load on the root and on the TLD servers. Now, if the cache is really long-lived, if they're very careful about it, maybe this could be only mildly bad. But there's always a risk. Someone's going to say, oh yeah, every time you hit this button on the phone, the root gets pinged. And then the root melts down in a fiery explosion. So let's not do that. This, by the way, was the problem with DNS Curve. Dan Bernstein's brilliant. And people act like I had some kind of thing against Dan Bernstein. Do you realize how hard I lobbied for his 1999 fix? Like, seriously? It's been like hours. Like, nope, can't do this one either. Doesn't work. Got to do what Bernstein said. The problem with DNS Curve is if you want this sort of end-to-end trust, and believe me, I'm just not interested if I don't have end-to-end trust. I'm not trusting some random box at Starbucks. Then you need, in DNS Curve, you can't use the local caches. You have to repeatedly trust some other host and go to the root, potentially. My answer to that was, no, I can't do that. So the other problem is Middleboxes. It's not like they're going to be very nice to you just because you're not talking to So the same Middleboxes that interfere with chasing will interfere with tracing. This isn't theoretical. I was at a hotel like 3 hotels ago. You got a problem when you define your life in terms of how many hotels ago it was. Yeah, those middle boxes, they'll do terrible, terrible things. Just show up on a network. Who knows what's going to get through? So I keep talking about Skype's law, and it occurs to me, what about DNS over HTTP? It's not a complicated suggestion. Instead of doing DNS over UDP packets that might get intercepted, what if we go over the Universal Tunneling Protocol, HTTP? If the net was frozen in 2001, let's use the one protocol that was not actually frozen in 2001. Now, I know what you're thinking. You're thinking, Dan, you and your tunneling. Yeah. But no, beyond that, you're probably thinking the performance implications of tunneling large amounts of DNS traffic over HTTP must surely be enormous. And by the way, I mean, this is implemented. This isn't a theoretical thing. It's in the Freebird server now. So how much does the HTTP tunneling slow things down? 10%? 20%? 50%? 90%? Well, so I got the actual data. It actually makes it faster. What? Yeah, apparently DNS over UDP, you'll get like 3,300 queries a second on this little box. DNS over HTTP, you'll get 3,900 queries per second on this little box. So it ain't slower, might be faster. Now Paul Bixby thinks I'm wrong. Like says, no, Dan, on big I internet, this can't possibly be the case. And he might be right. Look, being wrong is fine. Being wrong just means the world is more interesting than you thought it was. It's cool. There's tons of stuff in this talk that might be wrong. Even with a significant penalty, though, SuperChase over HTTP should actually work pretty well. And so within the next couple of weeks, Recursion Ventures is actually going to put a DNS over HTTP service up in the cloud. You know what? DNSSEC has to work. If it means we've got to help people tunnel their way to get DNSSEC chains, well, bring it on. Wrapping. Wrapping is cool. So there's this Kiwi, New Zealand guy. For those not in the know with the Kiwi name. Brett and I basically sat on the phone for about an hour and a half. And Brett's a real skeptic about DNSSEC. So was I. So we got along well. And Brett says to me, you have to be willing to separate the content of DNS from the transport of DNS. I'm like, that's actually a very interesting observation. So this led to an interesting concept. When you connect to a website, a secure website, the certificate is delivered to you over SSL, and you can sort of trust it. We basically had to deal with the realities of SSL certificate authorities, where they're a little bit hard to work with, and their security value is limited because there are potentially hundreds of them. They've sold off the rights to issue certificates thousands and some unknown thousands numbers of time, and you can't exclude the bad guys. If you, at the end of the day, VeriSign gives you a domain for a certificate, so can GoDaddy. So if you want more details on what's wrong with X509, I'm not going to recapitulate my talk from last year, but there's a reason why we're not all using certificates every day. Turns out, X509 can carry the DNSSEC chain. Look, SSL already moves X509. Might as well put some DNSSEC inside, giving us DNS over X509 over SSL. Take that, hotel mini boxes. It turns out this is not just a very powerful way to get through networks and get the DNSSEC chain out through any kind of firewall. It also is really fast because you're basically inlining the trusted information. Only before the trusted information had an indefinite number of forms. Now it's just give me the DNSSEC trust chain, period. Implementing this requires two things. First, you have to actually extract all the necessary records. This wasn't too bad. I got that working. But taking this morass of key material and saying, please draw a graph through it all so that you end up with this information get back at the root. This takes some work. LDNS keeps thinking it can go off and talk to the network. I want to just use the key material that I gave it, or throw it all away. So I'm still working on it. Nothing really I can do. But you know what's a totally different option? Well, you could just be Google's Adam Langley. Who's Adam Langley? Well, Adam Langley is one of the engineers working on Chrome. You know what I got this morning? I got access to a custom private build of Google Chrome with DNSSEC embedded. Yes. So here we have a site, and this site's online now, DNSSECEXP.org. The lock is there, the text is green. When you look at the cert, there is in fact DNSSEC material embedded. Now, I want to give a caveat. This is an unofficial private build of Chrome. Google is not at all committed to DNSSEC, DKI, or X509 certificate embedding. This is just Adam and I seeing what's possible. That being said, this is awesome. Google Chrome, DNSSEC, yes. And now I think it's good to start talking about actual applications. So where do we start with implementing domain key infrastructure? Well, we started this talk with FreeShell. FreeShell is federated identity for OpenSSH. It is based on the idea that you shouldn't log into a server with your public key. Your public key is a mass of random bits. You should be able to log in with your identity, or at least your email address. What ends up happening is the authorizer, in this case a text file called authorized keys 2, but it could actually be an LDAP backend as implemented by FedSSH. What happens is the server knows, okay, here's an account. Let's see who's allowed to come in. Okay, you're claiming that you might be one of these users that's trying to come in. It will look up in DNS the actual public key that you're supposed to use to get in. And how does it know that this public key it looks up is actually yours? It's able to simply check the flag. By the way, when I did the end-to-end resolve, when I went ahead and directly got the key material for this SSH public key, did it chain back to root? Not did I ask anyone else, not did I hope for the best. When I got the key material, does it say, this is in fact Dan at remotesupport.org's key? Is it him? If so, I let him in. If not, I say no. This was built in a couple of hours. This was not complicated. Guys, we have been suffering through broken federation systems as an industry. Everyone here might not know what federation is. So let me actually explain that as well. Grammar. So there are thousands, tens of thousands, hundreds of thousands, millions of organizations in the world. The old model of how computer people thought the world worked is all you need to do is talk to people inside your own organization. You know who's not inside your organization? Customers, or suppliers, or business partners, or vendors, or contractors, or temp agencies. When you're a company, that which is inside and that which is outside can get kind of blurry. It's just the way it is. And so one of the things we need is the ability to operate across organizational boundaries. Now note, email just works fine. Have you ever been on those threads where everyone ostensibly works for the same company, but there's like 20 different email addresses at the end of everyone? It just works, right? Why? Because email is fully federated, meaning it operates across organizational boundaries without a care, because everything chains back to the same root. Now you want to encrypt anything and things go to heck because we have no key material. But you want to just send messages, it works. Federation at its core is about being able to interoperate and interact with identities outside your organization. When I showed you that SSH demo at the beginning, what I was showing you is there's a customer, and he's got a network, and he's got a device on that network. And that device on that network has no idea who you are as Dan, or as Bob, or as Jim. It doesn't even know who this remotesupport.org company is. But you know what it knows? It knows, hey, I got to trust someone from there, and I can go to DNS to find out if I'm actually speaking to them. Done. This did not take a lot of work to implement, but it is actually fairly revolutionary. Here's why. There are 3 choices in normal federated systems. The first choice is called end-to-end complexity. This means is every company needs to do explicit negotiation with every other company to figure out just how much access they're going to give each other to information. And it's miserable. It's utterly miserable. It is very expensive. And it leads to a very precise outcome. I believe that if you're going to make claims like I've been making, you have to be able to show examples. On Gmail, if you receive mail from PayPal or eBay, the email looks different. Well, that's nice. That's 3 companies that have a relationship. That's about as far as our present-day technology has been able to get us to scale. End-to-end complexity got us 2 to 1. How do we get the rest? Well, the next option is the risk of kingmakers. In kingmakers, one group is trusted by others as the identity manager, and everyone's got to hope that guy doesn't turn into a crazy taskmaster. Give you a hint. He always turns into a crazy taskmaster. Final thing is what's called key bleed. This is what's happened with the certificate authority system. Effectively, there's a bunch of people with equal powers over assigning keys. One guy wants an advantage over the rest. The security level drops little. Now, one guy wants an advantage over what's remaining. Security level drops little. It's a race to the bottom. Whether or not people have the best of intentions, give it 15 years, and it's going to be broken. So that's kind of how federation has been failing us thus far. What is interesting in DNS, what is interesting in DNSSEC having a root, is we have a 4th model. We refer to it as the silent overseer. ICANN is a very interesting organization. And by interesting, I mean totally and utterly constrained by a huge number of external political constraints and actual straightforward technical limitations on what they're able to do. Now, that's not saying they can't do anything, because they can and have done tremendous things. Like, for example, shepherding the actual root getting signed. But if you compare the powers of the normal master roots out there, and then ICANN, man, I know which one I want to have to worry about. I'm going to worry about the guys who can't act to hurt me. So that's what's interesting. That's what makes domain key infrastructure so powerful. It is federation that will actually work. So what do? Do we add LDNS or lib unbound to every package out there one by one? Oh, you know, eventually, possibly. Maybe the operating systems will actually give us some functionality, give us some inherent caching. But what do we do in the short term? I don't want to write patches for everything. On Linux and Unix, SSL is handled via OpenSSL. And OpenSSL has a single function called X509 verify cert. That is a nice and self-contained library call. One function, one position. This is what says whether an SSL connection has been accepted or not. Could we do something with that? Yeah. We can build something called Freeload. Freeload is a DNSSEC verification engine that can actually be applied with no code modifications to pretty much every app on Linux and Unix through the LD preload functionality. There is prior work here. Russ Mundy at Sparta has done some tremendous work with LD preload using what he calls libval shim. Excuse me. There it is, libval shim. Libval shim also goes ahead and runs in front of applications and says, oh, you're doing stuff, let me DNSSEC that for you. But what libval shim does is it DNSSECizes the DNSSEC operations. So when it looks up an address, when it looks up a text record or this or that. And so you can get a lot of assurance that the addresses you look up are safe, the IPs. There's lots of ways that IP addresses can be manipulated. I think 13 was the last count. It's a kind of an exercise you do with the kids learning security. Talk about all the ways to hijack an IP address. Very cool work for its time. The other thing that it did was Mundy's work was done assuming that the root would never be signed. Because frankly, for quite some time, it looked like the root would never be signed. So it doesn't do all the chasing and tracing and complicated stuff. It just says, I assume if I'm looking at foo.com, I know how to recognize foo.com. Freeload is different. First of all, it does chasing. And second of all, it operates at the precise layer for the precise applications that are attempting to achieve end-to-end trust. It hooks SSL, not DNS. And it says, we're going to make sure that if an application is trying to make a secure connection, that what it speaks to, that the certificate validation process goes through a DNSSEC validation path. So, what does this look like? Here's curl without freeload. Curl is going to go ahead and it's going to try to connect to https://hospitallink.org, and curl is going to vomit a huge amount of error messages at the screen, and the last thing the user sees is the last line that says, use the -K or -- insecure option. Because one option for turning off certificate validation wasn't enough for users. They had to have two to make sure the user didn't send a complaint mail. Okay, so that's lame. You know what would be awesome? If you could just put the fingerprint of the SSL certificate in DNS, and now when you connect to hospitallink.org, the fingerprint is looked up and it says, oh wait, this certificate I see, you know, it may be self-signed, it may not go to any certificate authority, but DNSSEC is cool with it. What does that look like? That looks like this. Curl https, hospitallink.org, and this is the story all about how my life got twisted upside down. So, but just to be sure, so you can see that this is actually working, if you export the variable DNSSEC debug equals 1, you will actually get a bunch of debug symbols or debug messages put out showing you the library interposing itself and injecting DNSSEC validation. If you go ahead, now what the schema is now, this is deliberately incorrect. There's a whole bunch of work from a whole bunch of people to figure out the exact right way to put that hash, this figure. So the deal is you have a certificate. When you summarize it, you get a fingerprint or a thumbprint, and it looks sort of like this. The question is, I can go ahead and for any name, I can get a value out. What is the best name to get the best value out? There are a bunch of ideas, but I don't want to go ahead and step on some people's toes, so just accept this is the wrong way. So, if we go ahead and we break the actual thing loaded in DNS, just to demonstrate, what we see in curl is curl stops working. Even though it's doing a lookup in DNS, the wrong signature came back, and therefore it is rejected. How cool is that? Now when we fix it, curl works. You know what else works? wget works. You know what else works? Postfix, Postgres. You want to do secure database-to-database communication? MySQL. Apache. Why would Apache be interesting? Well, you know there are these things called client certificates. In client certificates, the server does not authenticate you. You authenticate yourself to the server. Now, client certificates haven't worked very well ever since they came out. And the major reason why is, how does a client certificate, which by the way might live on a smart card, how does a client certificate you get from one site work on another site? Well, this is a classic federation problem, and federation has been a disaster. Now it's very easy. You just look at the name you're offered. It's like, oh, you claim to be Dan at recursion.com or recursion.org for now. Let's go to recursion.org. let's see if you actually have the key for recursion.org. Let's see if that works. There is so much development to be done. This is why I'm interested in DKI. But let's keep the focus on browsers, why don't we? OpenSSL is great, but browsers don't use it. Internet Explorer uses Crypto API. Firefox and Chrome use NSS. Also, there's no LD Freeload on Windows. What to do? Well, there's HTTPS Proxy. PDP at Gnusis and actually put together a small little application that dynamically generates the appropriate certificates such that on a man-in-the-middle secure proxy session, SSL can be interposed. The way it works is that you basically tell your browser, hey, this proxy, it's got a root cert, it's God, you can trust it, it's cool. Based on the work of Uzuki Hisao and Andres Riancho and Dave Itel. Now what is sent over the wire on a secure proxy link is connect, www.site.com, a port, and then HTTP 1.1. What's interesting is that is enough for us to build what I call Proxy. Proxy is a remote validation proxy for production browsers. So we can provide clients, just as before, a custom root certificate. Before the SSL connection is established, we get the name of the domain the client would like to connect to. For each connection, we can provide a custom root signed certificate. Remember, wildcards don't work nearly as well as they used to. Sorry about that, we broke that last year. The browser will trust us. We, however, will only proxy if the real server passes SSL validation. Now, of course, we're running Freeload. So for us, passing SSL validation includes passing DNSSEC validation. And what do we get from this? We get the browser lock in IE out of DNSSEC. And we get the browser lock in Firefox out of DNSSEC. And we get the browser lock in Chrome out of DNSSEC. Not sometime in the future, we get it today. There's a neat trick. Remember no religion? There is something very sneaky we can do once we've outsourced validation. And it doesn't involve DNSSEC at all. In fact, it barely involves DNS. Wouldn't it be nice if we could bootstrap trust with nothing but a domain name? Well, we could have a self-certifying URL. I didn't say it's pretty. You can even put it in front of an IP address. No DNS at all. About 152.151. Now, this would seem kind of strange. I actually based this off of something called the self-certifying file system. Some other guy came up with a very similar idea in 1999. Leo Bernstein did his stuff. Guy gave SFS HTTP, which is what I was going to call it, and his name was Michael Kaminsky, and Michael's my middle name. Weird. There are some scalability issues. Links do work securely, but man, if that cert's ever lost, you lose access to content. But still, it's kind of cool. So at this point, most people think it's time to get rid of the certificate authorities. Oh, no. Actually, it turns out CAs are more valuable than they have ever been. Because in the real world, we have two different things. We have domains, bankofamerica.com, procterandgamble.com, yahoo.com, and there are brands. Bank of America, Procter and Gamble, Yahoo Incorporated. Brands are a closed namespace, meaning if you have Yahoo O or Yahoo Dash, guess what? That's still Yahoo, and a court's going to shut you down. So brands are closed in a way that DNS technically cannot implement, but certificate authorities can, and certificate authorities have. They've come out with a product called extended validation. And what extended validation involves is actual people in actual jurisdictions all over the world saying, yes, this group that calls themselves Bank of America are actually Bank of America. And then you get a green bar, and then you get a thing that says Bank of America Corporation and a country. And this is good. but not perfect. 2008, Adam Barth and Colin Jackson come out with Beware of Finer-Grained Origins. Very nice paper. 2009, Mike Zussman and Alex Sodorov do it 100 times better and basically implement what's called SSL rebinding. Their basic concept was, hey, if you have a site with an EV certificate, it gets a green bar. But if at time A, content is loaded from the good cert, the big cert, the expensive cert, and at time B, content is loaded from a not so expensive cert that happens to have the same name, the content streams will mix. And you will get attacker content from a bad cert, from a cheap CA, that is going to interfere with the good stuff. And there was no fix. There was nothing that the industry could ever do about it. Till now. DKI actually fixes this issue because of what's called the exclusionary property. DKI is built on DNSSEC, DNSSEC is built on DNS, and DNS excludes. When your DNS domain is registered through enom, GoDaddy cannot interfere with it, but when your X509 certificate comes from VeriSign, GoDaddy can interfere. It can issue a second cert. DKI by its very nature allows you to not just say, this is good, but this is the only good. If that only good certificate happens to be the extended validation one, well, we're cool. It's good. Nothing else will work. Now, what about the so-called invisible domains? Your average website is hosted from lots and lots and lots of other subdomains. What about those things? How do we deal with that? Zussman and Sodorov actually showed if you break one of the invisible domains, you also get compromised. Well, DKI deals with this two ways. First of all, we make it really easy to deploy SSL even on content distribution networks. If you've got a server with 100,000 domain names, guess what? Your name server can be configured to every single one of those domain names, always return the same hash. So it's always the same cert. It just works fine. SSL just got way easier and cheaper to deploy. You want SSL everywhere? You make SSL 1/10 the cost of actual operational deployment. Second, exclusion works for those invisible domains as well. So once you have those 1,000 hashes in DNS, if a random CA goes ahead and tries to throw its stuff in, none of them work. Before we finish, don't stop me. I'll go no more than like 2 or 3 minutes over at worst. Before we finish, I do believe we promised to do something about email. Anytime I talk about email, everyone loves PGP. Fine. We'll go ahead and patch DNSSEC into PGP. So we're working on a package called FreeGP. FreeGP ports end-to-end DNSSEC lookups to GPG. This is what it takes to do it. Echo, foo, pipe, GPG, no default keyring, temp, GPG, random, encrypt, armor, auto key, locate, PKI-R, test at pba.org. If you were to type that in on the modified GPG engine, you will, in fact, get 0 prompting, 0 notification. It'll look up the key, it'll validate it by DNSSEC, it'll encrypt, and it'll be great. Why am I not showing you Thunderbird right now? Because, man, GPG does not want to be secured by DNSSEC. Among other things, you know PGP certificates don't actually name the email address that they're signing for? And I'm sure, John, that there's some very, very good reasons why this is the case. But let me tell you, when I see a signature, I can read it. You know what I'm reading? The person's name. This is not supposed... What, we're back in the days of X? So this is, for all sorts of technical reasons, it's a really big pain in the butt. In order to actually get this working, deep work is going to be necessary, either with the NIG-mail or with like the PGP desktop stuff. Now what about DKIM? DKIM is kind of neat. DKIM is a way of putting not actually a certificate, but a public key in DNS. And it is a way for two mail servers to identify one another. To say, oh, okay, you're sending me this message, and I know that you're actually sending a message for yahoo.com because you've signed it with the Yahoo key, and I looked up the Yahoo key in DNS. If there's anything that you would think would be perfect for DNSSEC to help, it's DKIM. Well, there's a little problem with DKIM. There's absolutely no user interface to it in the world right now. Maybe there could be, but as a note, DKIM has no facility to authenticate not merely the mail server, but also the user at play. DKIM just doesn't do that. Right now, it is fundamentally an anti-spam system, not a replacement for generic secure email. So what else could we do? SMIME. SMIME is very interesting. Doesn't exactly have the coolest reputation out there, but it is actually the most widely deployed secure email system on the planet. It is in Outlook, which means it's in pretty much the entire Fortune 500. It's in Thunderbird. It's not in Gmail. The Gmail plugin doesn't do signature verification. If you don't do signature verification, I'm not talking to you. But SMIME has key management problems. Like everything built on X509, certificates have key management problems. It's not its fault. The big thing that really kills SMIME is lack of exclusion. You yourself may build a company that has the world's greatest key assignment system. Man, if you want a certificate from them, you have to go in, you have to prick your finger and deliver blood before they'll give you that pack of bits. Okay, that's cool and all, but the other guys that are just to do a DNS lookup, they can go ahead and issue a certificate too. And when they issue an email certificate, it looks just the same to everyone else on the rest of the internet. So it's the problem we had with SSL search for browsers, 100 times worse for email clients, and ultimately very few places have actually deployed the technology. So can we fix this? Literally, can we? Do we have the technical means? We were able to hijack OpenSSL because of LD preload. We're able to hijack the browsers because they have a piece of proxy functionality. How are we supposed to hijack Crypto API? I mean, it's got an extensibility point for rejecting certificates through its revocation engine, but it does not have a way to say, I want to write a plugin that accepts certificates. Now, maybe I could write a custom Outlook plugin, but that stuff's really undocumented. There is another trick, but it's way too hideous to talk about. Guess we're hosed, right? So, who here can recognize this astonishingly bad idea? No one? Aww. So, there's this thing in, especially the Windows world, called API hooking. It is normally used to cheat at video games. Oh yeah, we're hooking crypto. We're hooking crypto in Outlook. So we're putting together a package called FreeCAPI, DNSSEC validation for Crypto API. Crypto API has a function called CertGetCertificateChain. If it returns true, the chain is valid. What's really cool is that you can inject code in anything and say, hey, I want to be called when this application calls CertGetCertificateChain. If you debug your injected function, you actually get full debug symbols just for where you are. It's I don't care about the rest of Outlook, but right here at this line of coding, you're oh, okay, so here's pcert info and subject and algorithm and public key and issuer unique ID. Okay, I'm not usually a binary guy. This is awesome for me, so give me a break here. So here's the demo. And this is the last demo I want to do, and I wish I could do it live. We have a signed email here from dan@thebank.org. You can tell it's signed because there are 16 pixels that put a nice little award on it. But it's signed. Suppose we go ahead and we use this actual tool normally used to cheat at video games, remote DLL. What if we go ahead and we inject our code in that adds DNSSEC checking to Crypto API? What happens? Bam! Doesn't work anymore because we didn't know. We only put in the checker. We haven't actually put in the DNS records yet. So what do? We go ahead, we go to the certificate, And we see it's got this fingerprint 46, OC, 1B, E3, so on. And we go ahead and in this overly simplistic, incorrect encoding, we put that in as dan.smpka, thebank.org. And that's now what's going to be looked up securely via DNSSEC. Now, we have mail from the bank, signed by the only key in the world that can sign it. It's about time. So, perhaps now we can apply more than 15 pixels for security and identity. This, my friends, is where EV needs to go next. This is how we fulfill our promise to users that we have been failing at for 15 years. The user experience around secure email has been pitiful. Why? Because our confidence levels in what we've been offering has been tremendously low. If there's a signature, it could have been easy. If the signature is broken, whatever, it's probably a misconfiguration. How do we do better than that? We use DNSSEC to strongly validate the actual key that's been used to apply the signature. We can be much more powerful, much more flexible. And once we get to the point where not only do we see that there's a signature, but it's an EV signature, we can actually show the user we have a very strong reason to believe this mail you got actually came from the bank. So, in conclusion, new era begins. The root is signed, the market is ready, it's really time to build, it's really time to break. Let's work on DKI and fix the net. That's what I got.